to Gauss-Jordan elimination. Let me tell you what it is right away. In Gaussian elimination, we got an upper triangular matrix. Thinking of a matrix along with the constants vector, a representation of a system of linear equations. In order to solve the linear equations, you had to do back substitution. As you shall see very soon, back substitutions are also row operations. So just subtracting the last row or a multiple of a last row from the previous row will eliminate the last variable, and that is like substitution. And that process can be codified in an algorithm, and that algorithm is Gauss-Jordan elimination. It will scale each row so that the pivot becomes 1. So let's go through that. In Gaussian elimination, we got the row-echelon form, which was an upper triangular matrix. So we proceeded further. We got the complete solution by back substitution and some tricks in the case of free variables. We also saw that the upper triangular matrix gave the rank as a number of pivots and the determinant, if A happened to be a square matrix, as a product of the diagonal elements in REF U. Back substitution, like I just said, is also an elementary row operation. So if you do those row operations also on the augmented matrix, you're not changing the solutions because row operations don't change the solution. Just to remind you, we had 3 of them, swapping any 2 rows, which we tried not to do, but we had to perform it in certain cases. The second one, multiplying any row by a scalar, scaling a row, we did not do it for Gaussian elimination, but we will do it for Gauss-Jordan. And adding a multiple of a row to another, that was the one that you used most of the time in Gaussian elimination. So this extension of incorporating back substitution into an algorithm is called Gauss-Jordan elimination. So let's look at it starting from our equations, x plus y equal to 5, x minus y equal to 1. So that gives you the augmented matrix x plus y equal to 5, x minus y equal to 1. And subtract the first row from the second so that this element becomes 0. Fine. That made the second element minus 2. And now you see the pivots as 1 and minus 2 in the beautiful cyan color. So the elementary operator there was to subtract the first row from the second. As you know, you just apply that to the identity matrix in the right dimension, 2 by 2 in this case. So identity matrix was 1, 1 along the diagonal line 0, 0. You subtract the first row from the second, you get a minus 1 there. That is the elementary operator. Now the second thing that we want to do is to divide the second row by minus 2 so that we make the pivots 1. So that is part of our Gauss-Jordan elimination. So just scale the second row by minus half, divide the second row by minus 2. So that's the second elementary operator. So multiplying these two elementary operators, you will get the total elementary operation, but we're not doing the multiplication yet, but you're applying these elementary operators in that sequence on the augmented matrix to get this augmented matrix now. Now subtract row number 2 from row number 1 so that all the elements above any pivot become 0. So you subtract row number 2 from row number 1. That means the first row becomes the current first row minus the second row. That is one way of looking at it. That I'm looking at my elementary operator. Another way of looking at it is just take the identity matrix, subtract the second row from the first row, you get a minus 1 there. So that is the third elementary operation. Now, what do we have here? Look carefully in the coefficient part now. That reads like an identity matrix. It is an identity matrix. So we performed a series of operations, elementary row operations on A augmented by B, and we ended up with I augmented by some vector there, and that vector is actually the solution. You will find the solutions right away in the augmented part, and that is Gauss-Jordan elimination. As we saw, these steps, even though they sound formal and maybe unfamiliar, they are the same as a back substitution. Think about it for a second or a minute or 5 minutes and convince yourself that this is identical to back substitution. So we get the solutions from the augmented part of the RREF. REF is row-echelon form. The second R there is to say that is a reduced row echelon form. So what you get is an upper triangular matrix in row echelon form in the Gaussian elimination algorithm, and that has become an identity matrix in the reduced row echelon form, RREF, in the Gauss-Jordan elimination algorithm. So Gauss-Jordan will give you RREF. As you have seen, RREF is an REF with some extra properties added to it. In REF, you already had 0 rows at the bottom of the matrix, and the pivot in any row is to the right of the pivots in the row above. Gauss-Jordan gives you RREF, so it has all the properties of REF, and then you have scaled all pivot rows so that the pivots are actually 1 unit pivots. Then you used the pivot row starting from the bottom. Whenever you had a pivot, you use that pivot, which has become 1 now, to subtract an appropriate multiple of it so that all the elements above the pivot have become 0. So you use the pivot to get rid of all the elements above it. So RREF is an REF with some extra properties. REF is not unique because depending on whether you decided to do row swap or not, you might get different REFs. But an RREF of a matrix is unique. You cannot get a different RREF regardless of whether you did row swaps or not. So that is called a canonical form. As you might have realized by now, there are certain terms that mathematicians seem to love. Canonical is one of them. Another one that you will come across is the kernel. Now that I think about it, canonical, the root of the word canon, and kernel of truth, they all have something to do with truth. I also mentioned right in the beginning that there is only one truth. Truth is singular, and mathematics is the language in which truth in this universe can be expressed. So it is probably not an accident that mathematicians actually love these terms. Well, that's a digression. But let's look at the algorithm now. What you will do, of course, is to run Gaussian elimination first and then do 2 more steps. Scale each pivot row by 1 over the pivot in that row to get unit pivots. So you have to loop over only the pivot rows now. But remember, you're scaling now. As you know, scaling will modify the determinant. So the determinant of an RREF is not the same as the determinant of the original matrix. Determinant is not preserved with or without the sign. Now, after having made all the pivots 1, you scale the pivot and subtract the scaled version from the previous rows above so that all those rows above the pivot position will have zeros. So kill all the non-pivot elements. And this step is actually back substitution. So that's another loop, but it is restricted to pivot columns. So RREF is the canonical form. So once you do the Gauss-Jordan elimination, once you have the RREF, you have the solution, especially if you have an identity matrix. If you don't get an identity matrix, that means the solution is going to be something that we can say it depends. So let's take a look at that. So RREF will specify the solution when the solution is available, which means the system of linear equation that you started from is not inconsistent. You don't have a 0 equal to non-zero. So if you have some AB after doing the RREF, suppose you get the identity matrix here, then whatever is standing here is going to be the solution. Because just read this augmented matrix and cast it in the form of a matrix equation, and that basically just reads I times x is this vector on this side, which is not the original b, but it's b prime. So you started with ax equal to b. You have now ix equal to b prime being whatever you have in the augmented part. What is ix? Ix is just x, so x is b prime. So to put it in a pithy sentence here, ax equal to b, which gives you the augmented matrix AB. Perform RREF, you get the augmented matrix I b prime, which implies that x is actually b prime, and that is a solution if you can get I. If you cannot get I, then we have to look at it more carefully. So let's take a look at what kind of RREF you can get for different shapes of matrices like square, tall, and wide. If a matrix is square and if it has full rank, that means rank is same as the number of columns or rows, then all rows have pivots. All those pivots can be scaled to unity, and those unit pivots can be used to get rid of everything above the pivot in each column. So what you will end up is the identity matrix. All rows have pivots which can be scaled, and each pivot column can be made to have only one unit pivot. Everything else can be zeroed by appropriate scaled subtractions. That means the RREF of a full rank square matrix is going to be the identity matrix in the same size. If it is rank deficient, then it becomes more interesting. Suppose R is less than n, the rank. So R rows will have pivots, R columns also, and by the property of REF, the 0 row is going to be below, and the top R rows will have pivots, and there will be an identity matrix there of size R, but it is kind of embedded in the matrix of the original size n by n. So the bottom n minus R rows will be zeros because those rows got eliminated by Gaussian elimination. So there will be n minus R columns in the matrix that don't have pivots. Those will correspond to free variables, and if the system is consistent, you will have an infinity of solutions. So the REF will look like an identity matrix and some free variable columns, but they may not be cleanly separated. It's not like identity matrix will be in the top left and the free variables to the right of it. It might be shuffled in. The free variable columns may be shuffled in, which is what I indicate by this symbol, bow tie. And below that, you will have n minus R, which is a rank deficiency. Those many rows will be just 0 rows. So that's the shape. Here is an example. So I have a full rank square matrix here. So the equations are consistent and independent. Just 3 equations, 3 unknowns. Full rank means they're consistent and independent. So AB is x plus y plus z equal to 6 and 2x plus 2y plus z equal to 9 and so on. Do the REF, do a couple of scale subtractions or additions. You will get this as the REF. Go ahead and perform the RREF. Scale the second row by half. You get 1 there. Scale the third row by minus 1. You get 1 there. So minus 3 becomes 3. And then do the subtraction from the previous rows. You get the solution standing right here. But what's more important, what I wanted to show you was that REF of the augmented matrix has an identity matrix standing right in front of you. And if you were doing the REF of only A, which is a square matrix, full rank, that has become the identity matrix. Now let's take a rank deficient case. In here, I have the third equation not independent, and that becomes a 0 row in the Gaussian elimination. And then you can do some scaling of the pivot rows and some subtraction. Since there is a pivot here, you can use that to make this 0, but there's no pivot here, so there's no way you can make this 1, 0. So you get some shape like that. But if you look at it carefully, you can see that there is the identity matrix standing here, 1, 0, 0, 1. But shuffled in between the columns, you have a column corresponding to the free variable, which is what I meant by this symbol here. Identity matrix shuffled in with the free variable columns. If the matrix is tall, again, we start with a case when the tall matrix is a full rank matrix. So let's see what's going to happen. Tall means you have more rows than columns. If it is full rank, then that means all columns are linearly independent. So all columns will have pivots when you do Gaussian elimination, and they can be scaled to 1, and all those pivots can be used to eliminate the elements that are above the pivots. So you will get a clean identity matrix near the top. What will happen to the rows that are below? What will happen is this. You have a 1 in the first column, 1 in the second column, and so on. Every single column has a 1 at this point. You can use these 1s in the pivot columns, scale them appropriately to subtract away and get rid of all the elements below the pivot columns also. So there will be a clean identity matrix and a 0 matrix below that as the RREF. So the bottom m minus r rows will become zeros because, as you know, only n rows can be linearly independent because the number of linearly independent rows is the same as the number of linearly independent columns, which was n. So the rest of them will have to become zeros. So what you will get in the RREF will be a cleanly separated IN, n being the number of columns, near the top and all zeros below that. When it is rank deficient, the situation becomes a bit more complicated. Now the rank is less than the number of columns, which of course is less than the number of rows because it's a tall matrix. So our rows are linearly independent because that's a rank. Our columns are linearly independent also. So that will form an identity matrix of size R by R identity matrix. In the top R rows, all other rows, M minus R rows will become 0 rows because they are linearly dependent. That's what the rank means. Rank being R means M minus R rows will have to be linearly dependent and they will get pushed down to the bottom of the canonical form. So there are n columns now. Only R of them will have pivots which have become 1 because of the process of Gauss-Jordan elimination. The rest, n minus R columns, don't have pivots and they are columns corresponding to free variables. But again, the free variables don't have to be cleanly separated from the pivot columns. So what you will have again is an identity matrix of size R by R, R being the rank, shuffled in with free variables. How many of them? The rank deficiency, which is n minus R. The rest of the rows, m minus R rows, will be zeros. So that is a shape, and these shapes you have to get used to. You have to understand this well enough so that you can reproduce it if I ask you questions like this in exams. So let's take an example here. We have 4 equations in 3 unknowns. So for the coefficient part, I have 3 columns and 4 rows. The REF looks like this. The first 3 rows have pivots and the last one becomes a 0 row. And it so happens that I chose the constants carefully such that I have a 0 equal to 0. So there are solutions for this one, a unique solution in fact. And what I see here is an identity matrix of size 3, 3 being the rank of this matrix or the coefficient matrix. And then my solution is right here, 1, 2, 3. X equal to 1, Y equal to 2, and Z equal to 3. Now, if I have rank deficiency, in this case, I have a rank of 2 for a 4 by 3 matrix, tall matrix, but rank deficient by 1. So M is 4, number of rows. Rank is 2, so 4 minus 2 rows, M minus R rows, have become zeros there. And by doing the appropriate scaling, I have 1 here, 1 here. That means this and these 2 columns look like columns of identity matrix. And in between, I have a column corresponding to a free variable. So that's the situation. Now let's look at a wide matrix. If it is full rank, then what's the rank? Rank would be the number of rows because there are fewer rows than columns. All rows are linearly independent, so there will not be a 0 row in the coefficient side. So the system of linear equations will always be consistent. And all rows, the pivots can be scaled to 1. But there will be more columns and n minus m columns will not have pivots. So they are columns corresponding to free variables. They may be shuffled in. They may not cleanly separate from the identity matrix that will result from the Gauss-Jordan elimination. They might be shuffled in and they will appear somewhere. So the situation is a wide matrix will have an identity matrix somewhere. Shuffled in along with the columns of the identity matrix, you will have the columns corresponding to the free variables. And how many of them? There are n variables to begin with. And the rank was m, so n minus m. That is a rank deficiency. That is the number of free variables. Now, if it is actually rank deficient, that would mean that the rank is less than the number of rows. So there are some rows that are not linearly independent. They will become 0 rows near the bottom. So originally there were m rows. The rank was R, then that means m minus R rows are linearly dependent. They will become 0 rows and get pushed down to the bottom. The rest will have pivots. If you look at the columns, there were n columns. Only R of them will have pivots. So n minus R will not have pivots. Those will correspond to free variables. And the number of free variables is actually n minus R. Again, the free variables may not cleanly separate from the identity matrix resulting from the Gauss-Jordan elimination process. So that is what is indicated by the bow tie here. The columns of an identity matrix of size R will be interspersed in the top part of the RREF with some columns that correspond to the free variables. In the bottom, originally you had m rows. rank was R, so M minus R rows are linearly dependent, and those rows will get pushed down to the bottom. Example here, first case, a beautiful system of linear equations, full rank matrix on the coefficient side. So this is the REF, there was a -1 as the pivot, which gets scaled to become 1. So you can see an identity matrix column here, another column here, and this guy is the free variable. Rather, that column corresponds to a free variable. And if you want to see a rank deficient wide matrix, I have widened it by adding one more variable and added one more equation. So I have W, X, Y, and Z, W plus X plus Y plus Z equal to 6 and so on. And after doing the Gaussian elimination, you will see that there is a 0 row, 0 equal to 0 in this case. And then you have a bunch of free variables. There's only one pivot here in the second row, and of course first row has a pivot, and then these two guys are free variable columns. What you will do is to scale this one by half so that that pivot in my red square becomes 1. That makes this guy also 1, but the last one becomes half. Then after this has become 1, I wanted to get rid of the elements in the column corresponding to that 1, 0. So I subtracted it from the previous row, subtracted row 2 from row 1, and that resulted in this kind of situation. What you can see in this case is a clean identity matrix here, plus a couple of free variable columns. It just so happened that my identity matrix got cleanly separated, but it did not need to be. These free variable rows might be shuffled in with the identity matrix columns as you saw before. So let's summarize this, shapes and the canonical forms. For a full rank square and tall matrix, there will be a clean separation of the identity matrix, and the 0 blocks will be the bottom rows. In the case of a wide matrix, even if it is full rank, the separation is not guaranteed. It might happen. The identity matrix, as we saw in the previous example, here the identity matrix just happened to be cleanly separated, but that was just blind luck. It's not guaranteed. If it is rank deficient, of course, you will have 0 rows and free variables. The separation between the columns corresponding to the free variables and the columns of the identity matrix is not guaranteed. It may happen, but it's not guaranteed. Now, just like we did row operations, you can also perform column operations without changing the rank. The row operations don't change the rank. Similarly, the column operations also will not change the rank, but it will change the solutions. What will happen is that as you shuffle columns around, the column corresponding to the variable X will become the column corresponding to the variable Y or something else. So the solutions will change, but the rank will not change because it's the same as doing row operations on the transpose case. So by doing column operations in this matrix that has identity matrix columns and the free variable columns shuffled in, you can group the identity matrix columns to the top left corner so that you'll get an identity matrix there. Look at the size of the identity matrix. That will always be R by R, R being the rank of the matrix. And since we did not change the rank using the column operations nor the row operations, the rank of this RREF extra is the same as the original matrix. And now you can clearly see that the number of columns with pivots, the column rank will be in the identity matrix R, and the row rank also will be in the identity matrix R. And that is another proof that the row rank is the same as the column rank. I don't think this proof is any better than our original proof by just looking at the pivots, but it's presented as another proof here and there. Now let's look at the solvability also once more with reference to the rank and the shape of the matrix. If it is a square full rank matrix, the rank is n, RREF is always the identity matrix. So we might say this differently. We might say that all square full rank matrices are row equivalent or column equivalent to an identity matrix, which means from the identity matrix, by performing a series of row operations or column operations, you can always get to any matrix that you start from. If that statement sounds mysterious, let me give you a geometric view of that. What this is basically saying is that if you have enough vectors, you can generate any other vector in the space. Remember, long time ago, we had 2 vectors, the blue vector and the red vector in R2 using those two vectors. By taking linear combinations, you could get to any vector in that R2. These two vectors spanned the space of R2 as a vector space. That is what this is saying, but maybe we are not fully ready to appreciate that, but that's what it is saying. Now, if you have a square matrix that is rank deficient, then R is less than the number of columns or the number of rows. Then you will have some free variables and some zero rows. It is possible that the zero rows might lead to 0 equal to non-zero depending on the constants that you started from. So the situation might be inconsistent, the equations might be inconsistent, in which case you will get no solutions. But if the equations are consistent, you will get an infinity of solutions. A tall full rank, again, the moment you have 0 rows, it is always possible to have 0 equal to non-zero, leading to no solutions. We were wise enough to select the constants vector well, then you might get a unique solution. Never an infinity of solutions, which is interesting. Tall rank deficient matrix, you have free variables. So as you can see, when you have free variables, you are free to choose the value, and that's when you have infinity of solutions. The reason why you did not have an infinity of solutions in tall full rank matrix is because you did not have f here, no f, no free variables. So the moment you have free variables, you can have infinity of solutions, providing that the set of equations is consistent and you don't have 0 equal to non-zero in the REF or RREF. Wide full rank, always infinity of solutions because there are free variables, because you have more columns, more variables than rows equations. So under constraint, always infinity of solutions. But the moment you have rank deficiency leading to a 0 row, that might turn out to be non-zero, in which case you will get no solutions, or infinity of solutions because you always have free variables. So go through this and watch this section of the video a couple of times to get this completely right in your mind, because it is important to see these things. So the next section will be about the inverses of matrices and when you can invert matrices, inverses and invertibility.